Hello, this paper presents time-frequency-based EEG motor imagery signal classification with deep learning networks. The authors of this paper are Mohammed Karam Moni Rabi, Robert B. Leshan, Dr. Said Belkasim, and Dr. AKM Kamrul Islam. Our team includes researchers from Bangladesh University of Engineering and Technology, North Carolina A&T State University, and Georgia State University. This research focuses on improving the classification of motor imagery EEG signals using wavelet-based time-frequency analysis and deep learning. Our study proposes a wavelet transform-based feature extraction method combined with time-frequency analysis for classifying motor imagery EEG signals. We specifically select channels C3 and C4 to capture event-related synchronization, ERS, and desynchronization, ERD, which helps filter artifacts and noise. We then convert the clean signals into 2D time-frequency images to train two deep learning models, a deep CNN and VGGnet. The models are evaluated on accuracy, loss, and training epochs using EEG dataset 3 from BCI Competition 2. Results show VGGnet outperforms deep CNN in both training loss and accuracy. Motor imagery EEG signals reflect brain activity when a person imagines limb movement. This activates the sensoromotor cortex and produces ERS patterns in the 8 to 30 Hz frequency range. However, EEG signals are noisy and non-stationary, making classification challenging. Deep learning has emerged as a powerful tool for this task. Our approach leverages wavelet transform for multi-scale time-frequency analysis without the limitations of STFT windowing, enabling effective feature extraction even from small or filtered datasets. Our methodology follows a structured pipeline. First, we select C3 and C4 channels to identify ERS patterns and filter noise. Then, we apply continuous wavelet transform to generate 2D time-frequency representations, which are converted into 64 by 64 by 3 RGB images. These images serve as input to deep learning models. Unlike STFT, wavelet transform avoids fixed window sizes and captures both time and frequency details effectively, making it suitable for small datasets. This flowchart summarizes our classification pipeline. Starting from raw EEG signals, we perform channel selection, C3, C4, noise filtering, wavelet-based time-frequency transformation, image generation, and finally classification using CNN or VGGnet. Each step is designed to enhance feature quality and model performance. We use two CNN architectures, a simpler deep CNN with 2 convolutional layers, and a deeper VGGnet with 6 convolutional layers. Both models were trained on the same image dataset derived from wavelet-transformed EEG signals. Performance was measured using accuracy, loss, and training epochs. Here are the key parameters used in our experiments. We split the data with 30% for validation, used a batch size of 5, and trained for up to 500 epochs. The wavelet filter used was the butterfly filter. Input images were reshaped to 64 by 64 by 3. These settings ensured consistent evaluation across both deep CNN and VGGnet models. These figures illustrate the training accuracy and loss for deep CNN and VGGnet. As shown, VGGnet converges faster and maintains lower loss values. The accuracy curves also show that VGGnet stabilizes earlier, indicating better generalization and efficiency. The performance comparison shows that VGGnet achieves higher maximum, minimum, and average accuracy compared to deep CNN. Specifically, VGGnet reaches a maximum accuracy of 0.90 for in just 20 epochs, while deep CNN requires 110 epochs to reach the same accuracy. In terms of loss, VGGnet exhibits lower minimum and maximum loss values, indicating more stable and efficient training. In conclusion, our wavelet-based feature extraction approach combined with deep learning provides an effective framework for motor imagery EEG classification. VGGnet, with its deeper architecture, achieves comparable accuracy to deep CNN but with significantly fewer epochs and lower loss. Future work will focus on deploying the model in real-time BCI systems and evaluating additional performance metrics. Our work builds on prior research in EEG signal processing and deep learning. Key references include studies on ERS discrimination, autoregressive models for signal synthesis, and hybrid neural networks for motor imagery classification. These are cited in the paper for further reading. The development of time-frequency-based EEG motor imagery signal classification with deep learning networks is an ongoing process, and we welcome any suggestions or insights. If you have any questions regarding this work or are interested in collaborating on future research in this area, please feel free to contact the authors via the provided email addresses. Thank you for your attention and interest.